you have this amount of carbon to remove and to burn, to oxidize into.
Yes.
Yeah? And you have 15 cubic meter oxygen, okay, per ton. So you see that you can burn everything.
Yeah, in the case, the energy from post-combustion
So in fact here
was
you have enough oxygen.
Yes.
This is the total oxygen, yeah? G82. This one here. Alright.
Yes, the air from air. Yeah.
From the air.
Time.
Plus the oxygen from refining.
Yes.
This one here. Yeah. From the total oxygen injection. Lances plus project. Yeah. Air plus cojet minus what is necessary for mangan and iron.
Oxidizing.
What is mentioned here.
Yes, yes.
So this is the oxygen available for carbon oxidization. And you
Yes.
see that clearly you have enough. Oxygen available.
Post-combustion.
You have even more because the remaining 7.6%.
Yes.
Yeah? That's why you can burn all the CO, which doesn't mean that the CO will be burned into CO2 in the bath. So, in the bath, for the thermal balance, we just consider 0.3.
Yes.
The rest of the post-combustion is done above the bath. Yeah?
Yes.
Right?
Yes. That's why the energy from post-combustion was taken into consideration, right?
Yes.
And I have one more question regarding the silica.
Yeah.
How much silica are there in scrap? I want to see just that one once again. Silica from the scrap.
Yeah, here.
3.2 kilogram ton. That also makes some energy, right? Okay. That's nice to hear.
If you want to see the energetic equivalent, it's here. Yeah?
Yes. 많은 것 같아요.
옆에 사람들 설명을 좀 해주고 그 진행 정보서를 작성.
내가 물어본 거 뭔지 알겠죠?
잘 모를 거야. 내가 느낌이 지금.
아니, 아까 저기 가면은 저기 리파이닝 란에 가스 성분이 CO가 제로가 되어 있었거든. 보통 이제 우리가 지금까지 얘기하기로는 CO가 논에서 일부는 반응하고 일부는 나가면서 반응하는 걸로 얘기가 되어 왔잖아. 계속 저기 미철도 그렇게 얘기를 해왔고. 그런데 이 데이터 상으로는 CO가 제로로 되어 있는 거야. 그 얘기는 일단 가정하기로는 포스트 컨버스션 안에서 다 일어나는 거라고 에너지 밸런스도 거기서 다 고려를 했다는 얘기야. 근데 나는 모르겠어. 그래서 조금 모순이 있는 것 같아서 내가 자꾸 물어본다고 사실은. 지금은 내가 뭐라고 나도 얘기를 못 하겠어.
온에서 포스를 달려면은 그 열량이 그 멜트 디스틸에 영향을 미칠까요?
사실 밑으로는 많이 영향을 못 줘. 어차피 나가는 가스니까 그게.
그러니까 플레임 생기면서 여러 가지 복사열도 있을 거고 그런 게 있을 수 있을 건데.
그거 물어봤고 한 개는 스크랩 속에 SI가 얼마인지 갑자기 생각이 나고. 왜냐면 SI가 저도 에너지가 요소는 얼마 안 되는데 전체적으로 그리고 C 빼고는 제일 많거든. 그래서 스크랩 속에 SI가 얼마 있는지 다시 갑자기 궁금해져서 물어볼 거라. 그래서 저만큼 에너지를 낸다는 거고. 오케이. 넥스트. let's go into the leather furnace.
All right. Okay. So again, you see you have different tables.
Yes.
First, we start with the tapping conditions. And you see, if you put here the tap weight, 40 tons, the ladle dimension is adjusted. Yeah?
Mm.
And you can vary the height on diameter ratio.
Yeah. By that one, we can finish the leather design, height, diameter.
Yeah. This is important for the stirring energy calculation.
This is a ratio? For the ratio calculation, that's
Where it is? Yeah, you have this ratio. Right
Okay.
now is 95.
이제 저게 그 레드의
Now is 85.
비율에 따라서 뾰족한 레들이냐 옆으로 넓은 레들이냐에 따라 가지고 그 이 한류되는 시간이나 한류되는 게 달라. 그래서 지금 상당히
Now is one.
좋죠. It's inside the diameter is inside of the laboratory.
Yeah, yeah. Of course, huh?
Yeah. But I check.
Because here I consider only the steel volume.
Still. Except also slag, yeah. Only steel.
Only steel.
Water straight.
Only steel.
Then leather height itself also.
Yeah, of course.
So here I have the EAF carryover.
Yes.
It means for this capacity, that means 4 kilograms per ton means 160 kilograms of slag. Of course, you have 150 ton, this is 600 kg. Yeah? And this is the slag, EAF slag analysis.
The EAF slag carryover slag means you the power out from EAF or do you charge them another carryover slag? What's the meaning of exact?
This is the slag
Yeah, carryover slag.
from the furnace tapped into the ladle.
Try to the leather.
Yeah.
Okay. Inside of the EAF.
Yes. This is not the slag you get on top of the ladle after tapping, because you put lime in the ladle already during tapping.
Okay.
But this is calculated later. Yeah? And this is the steel analysis.
Okay.
Then we calculate the alloys, where you can put here the aim composition with the minimum and maximum. And you can calculate according to aim or according to minimum. Yeah? So
we can change the aim value and minimum value of the additives.
this you can change. Yeah?
Yes.
If I remove this, you see you have a small, let's say, advice that you have to calculate the alloys. Now, alloys are adjusted. If you can calculate to minimum, you have another calculation. And you can put the cost here of the alloys and you get the overall cost. And this is what is optimized.
Yes.
The cost is optimized. Yeah? So if you don't have cost, you cannot run this calculation. Huh? And here you have the fluxes, and it tells you that the flux are not adjusted.
What does that flux is not adjusted? What does that mean?
Excuse me?
What does that mean? Flux are not adjusted.
What is your question?
Fluxes are not adjusted.
Yes.
What's the meaning?
What is flux? What is flux according to you?
Rhyme dolomite.
Okay. And what means are not adjusted?
So that means
It means
you need to adjust
it
it.
means these
No?
values are not correct.
Okay, I see.
Like here, the alloys are not adjusted.
I see,
Okay.
I see. Yes,
All right.
yes.
So to adjust the flux, we have to go in this sheet. Well, so you combine slag analysis and deoxidization, because of course the deoxidization products will go to the level slag. Okay? So this is what oxygen we had in the steel, and okay. Yeah. So we have the ppm of oxygen from the steel, which are 100 kg of oxygen. And this is the oxygen fixed on FeO and MnO, yeah, from the carryover. So this is the total oxygen we have to, because this is a calculation, yeah. This is the total oxygen we have to remove in terms of kilograms. Yeah? So then you have the deoxidization calculation with aluminum killed or with silicon killed.
Okay.
Yeah? Silicon killed allow a certain amount of aluminum. Yeah? So then I have the proposed composition for aluminum killed steel and silicon killed steel. This is standard analysis. Yeah? You see that each time I have some Al2O3, even for aluminum silicon killed steel. Because I don't consider the use of fluorspar. I know that, for example, in China, fluorspar is allowed. They put a lot of fluorspar in the slag, and they don't have aluminum at all. But in some other countries, like Germany, for example, fluorspar is forbidden. France is close to be forbidden as well. So people are trying to use, let's say, alternative solutions. So alumina is a good solution.
뭐가 금지됐다고?
P.
플로어. 아, 아니.
Fluorspar.
플로어. 야, 플로어.
CAF2.
CAF2. It's forbidden in Korea also, but it is needed in stainless steel and steel in plant. So it's small.
Yeah.
Use it.
Yeah.
CAF2가 뭐예요?
플로어 형성.
So here, then you put the analysis you want to have according to, let's say, this ternary diagram. This represents the well-known famous ternary diagram with the wait a minute, SiO2 on top, CaO, Al2O3.
So in Europe, you use the P instead of the floor.
P.
What did you do? What do you do?
Alumina.
Alumina.
Yeah.
What
What is P?
phosphorus.
Phosphorus.
No. Either you use the alumina for the
You
melting.
want to use phosphorus in the ladle furnace?
No. No
Yeah.
use it. Okay, I want to hear how to use the alumina instead of the pro.
So you have different kind of alumina. You have the premix and pre-melted slag, which is rich in alumina, and of course it's composed of calcium aluminate, and of course you have to cut back the lime amount in case you are using this, or directly alumina powder.
Alumina powder.
Yeah.
Okay.
Or aluminum ash.
Aluminum acid.
Yeah.
Is it also stainless steel? Is it also stainless steel?
Stainless steel. Oh, there is no more stainless steel production in France.
Okay.
The stainless steel plants has been shut down.
Oh, okay. I see. Competition.
No, I mean they have been purchased by, let's say, a big company, and they have rationalized the production. So all French production has been shifted to Belgium.
Okay.
Yeah. So you put the analysis you wish here, and of course it's not possible to calculate easily the sulfur partition coefficient. Yeah. So this is input. Yeah. I haven't been smart enough to make a formula for the sulfur partition coefficient. If you have good methodologists who have an idea, it will be welcome. Yeah. So in order to have a guideline, here on this ternary diagram, you see the partition coefficient 500, here 200, and here 100. So, if I change, for example, I put here 25, of course I have to remove something, so the alumina will be penalized, so I will put 12 and MgO 7. Okay, it's a bit above 100, but the system will, let's say, adjust it by itself. The K is the well-known as well basicity coefficient for the ladle. Yeah? It's E15 lime divided by plus the 2/3 of magnesia divided by the alumina plus silica plus half of the this stuff, the other stuff. So then we adjust. Okay, then we don't have the right stuff, so we have to start again. Balance of MgO is negative, so we have to decrease the carryover or decrease the MgO of target analysis. So that means we have to put 8%. Decrease the carryover, increase the total target analysis. Okay. So it's not enough. But now it's good. Yeah. So now our point is right there. Yeah. But we can as well decrease the line and then the point will go on this side.
양쪽이 고형이지, 고형. 양쪽에
예,
있으면.
솔리드 파이.
그렇지.
Okay, here you have the fluxes, and now the flux are adjusted. Okay. So silicon calcium is for the slag deoxidization. Yeah. And then CaO, MgO, illuminate, and slag. It's the product. Huh? You have 10 kg per ton, which is low, huh? But it's okay. And here you have the mass balance. Yeah? This is the total slag. This is coming from the carryover. These are the products of the deoxidization, the refractory consumption, and the additions. Additions, this is all this stuff.
In case of the lead furnace, the carryover slags, we have to receive the data from the EAF.
Yeah. Yeah, this is not a dynamic model. Yeah? This is just to let's say design the leather furnace. Yeah. To know how much, roughly how much, let's say, product you need to dimension the silos, and then the stirring, the flow rates.
Yeah.
Yeah.
So if when we supply only the leather furnace, in case of that we have to receive the carryover slag compositions from the EAF or existing rejector. All the carryover slag.
Yeah.
Okay.
So there you have nothing to do because it's already calculated with this criteria for soft bubbling 150 watt per cubic meter, for alloy and heating 300, and for deep desulfurization over 500. So the fluxes are calculated here, depending on the ladle capacity and ladle height and diameter, according to this formula. I have not invented this formula, this is on literature. Right?
메이트 제곱을 안 했구나.
So,
what is the 500 watt for the desulfurization? Yeah, the 500 watt means it's a losses.
watt per cubic meter, this is the stirring energy.
Stirring energy.
This is given by this formula.
Stirring energy need at least need the minimum.
We are
stirring energy.
We are talking about stirring energy.
Yeah.
Energy, what is the unit of energy?
Okay. I confused the EAF losses.
No, forget. We are in the level furnace now.
Okay.
Yeah?
Okay.
So, stirring energy is given by watt per cubic meter.
Okay.
Yeah? And the watt per cubic meter are calculated according to this formula, where Q is the flow rate, MA is the ladle capacity in tons, and H is the height of liquid steel in the ladle. Yeah? Underneath, this is the mushroom height. When you stir, you make a mushroom,
Yeah.
and this is measuring, evaluating the height of the mushroom. So, where H
지난번도 지났으니까.
is the metal height, epsilon is the energy of stirring, and V is the V is the flow rate. Yeah. So the blue line is the stirring energy, the red line is the mushroom height, and the green line is the distance between the mushroom and the electrode.
주문이 뒤에서 펌프 용량이라는 얘기를 하는 펌프 용량.
무슨 pom프?
깨서 밀어지는 펌프 용량.
아니 그런 게 아니고 이게 스트링을 이거 밸류를 시키려면 이제 기본적으로 스트링 에너지가 필요하잖아. 그 에너지 계산하는 그 에너지 계산하는데 밑에 이제 노멀 리터 per minute 나오면 제 분량이 이제 결정되는 거지.
그냥에 따라 갖고 밑에서 밀어주는 에너지를 얘기하는.
그렇지, 그렇지.
그거 펌핑 파워라는 얘기.
펌핑이라고 하기는 좀 그렇지.
지금 스터링은 저것도 돼요. 그냥 매그네틱 힘으로 이렇게 또 그것도 되는 거죠.
아,
그러니까
그건
그걸 에너지로
매그네틱은 안 쓰니까.
그러니까 그걸 에너지로
쓰는
쓰는
있어.
그 힘.
오케이.
덤플링으로.
이렇게 플러스 오케이.
This is just to cross-check in case of a small, sometimes you have a very small ladder. This is to cross-check that the electrode regulation will not be disturbed by the stirring. Because I had this case several times. Then we come to the desulfurization. Because for desulfurization, here, desulfurization rate and final sulfur, the time is very important. Yeah? So we have to consider all the time where the steel is in the ladle. For tapping time, transfer for ladle furnace, first phase of heating, then some power off, for example, return of analysis, then main desulfurization. So it's combined here because I assume it's power off. Yeah? And this is the second heating, and then soft bubbling time for the inclusion decantation, and then the transfer to CCM.
지금 요즘 몇년 8년 많이
밑에 성공 구조 어디?
퍼센테이지.
So you see, this is input data. Customer wants to have 4.5.
The heating rate in one of customer asked that the normal heating rate for Celsius per minute, normal 4 degree per minute.
Yeah.
But they want max heating rate is 5 degree per minute.
This is stupid.
And yeah, they use the 3 taps. Yeah, it's just 4.5, 5 degree per minute. And they want to increase the temperature 5 degree per minute. Yeah, they do not edit anything. They only the heating. So if we the select transformer capacity, same transformer for the 4 degree per minute. Yeah, and we can use the 5 degree per minute without any charging alloys, without any additives.
No. This heating rate is all the time done without any alloying.
This is without alloy?
Of course. When you talk about heating rate, how can you check an heating rate whenever you allow yourself to put some stuff in the ladle? How much? Is it flux? Is it the oxidization? Is it mangan? Is it molybdenum? What is it? So whenever you talk about heating rate, it is all the time without any addition.
So when we check that we compensate the alloys -1 degrees and so on.
No, forget it. It's stupid. No.
In your case, it's the heating rate is only 40.5 minutes. It's
without alloys. When you talk about heating rate, never allow the customer to put alloys. Otherwise, you have to fight for hours about what is the influence of the lime, what is the influence of... Is the steel already pre-deoxidized or not?
Yeah. But
it's simple.
Okay.
No alloys. I have 5 minutes.
Simple. But
I have 5 minutes heating time. I measure the temperature before. 5 minutes heating time. Temperature after, and then I have the kilowatt hours. I have the temperature and
in case of the EAF steel making, it is simple. Why? They can put in, they can cut the freeze the molten steel and they cut it and they use a scrap. But in case of BOF, they do not want only the heating rate. Do not want to check the only heating rate. You know? Without additives.
I don't catch you.
In normal the BOF steel making, yeah, they want to they do not want to make the molten steel, yeah, to the scrap, and they want to operate it, and they want to compensate how much alloy is put in, and -1 degree, -0.5 degrees, and they want to check it like that.
No, but we are not steel makers. We are furnace suppliers.
Yeah.
So we run the test once. We give a guarantee 4.5 without any alloys. Afterward,
Yeah.
of course,
Of course. you are
customer
right.
has his own practice, but we just have to demonstrate once to get the FAC that the ladle furnace is able to reach this ratio. That's it.
Of course, you are right, but in our case, we have to do it like that. And okay, we have the experience. Okay, it's the problem. But I want to know that if they want, one of my clients, they already prepared some pre-project, and they already 3 taps. Yeah, 1 tap is 4 degrees per minute. One tap is 4.5 degree per minute. One tap is 5 degree per minute. They use it now, so they ask to me, like with their existing plant. So, and at that case, we have to calculate the transformer capacity to 5 degree per minute, right?
Yeah.
Okay.
If this is a customer request, you have to follow.
They said 5 degree per minute is in only emergency case.
It doesn't matter. We don't pay the refractory. They pay the refractory.
Yeah. Okay, I know, but we have to.
If they want 10 degrees per minute, we run 10 degrees per minute.
But we also supply the bigger transformer. That is the problem.
But they pay for the transformer.
I don't think so.
Why? You have to give them the transformer.
Yeah, we supply the transformer. We will supply the transformer.
But they will pay for it.
Yeah, I know. But they want to buy the same price, and that is a problem. Okay, keep going.
What is the ladle capacity?
Ladle?
Yeah.
330 tons.
330 tons. My God. Yeah, it's a big one. Huh? 330, yeah?
30, not 50, 30. Nangan.
He doesn't want to.
Aim.
I cannot reach the mangan because I have too much carbon. No, see,
Change the aim. Same.
Aha.
진짜가 못하는데.
See, coming in. Okay. Sometimes the solver has a stupid idea, so you have to unlock the system, because it's too far away from the solution. Okay. So we need 5, eh?
First time is 14, 13, 38, 14.
What is the process time?
First time is tap to tap time.
Yeah.
Yes. 30.
30?
Yeah, 30 or 40. 13.
Including tapping time and transfer, etc.?
No. 30, yeah, 45. Okay, 45.
Oh, done. So what is the transformer? So you need an arc power of 38.6 megawatt.
Yeah, it's good. Oh, 54 megawatt?
120 MVA.
Really?
Yeah.
쓸데는
The existing 45.
Eh?
Yeah, the existing is 45.
45 for 330 tons? You need 55 megawatt. Okay? Ah, yeah. Okay, I see. Yeah, okay, wait. This 120 MVA, this is coming from here. Because the criteria I'm using is to keep the refractory index below 60. So you have different, you see different scenarios here. My favorite is, let's say, this is given by the slag thickness. Okay. Slag thickness, I have 17 kg per ton. So that gives me 66 millimeter according to the ladle dimension.
Height, how about the height of the slab?
66 millimeter.
66 millimeter?
Yeah. So to get 66 millimeter arc length, I need these settings. Okay? But you have other possibilities, you see, because this is manual. Yeah? Then I have a huge step. Okay, I have only 44 MVA. Yeah? If I give 45 kiloamps, I get 46 MVA. If I go, I want to go.
우리 몇 가지 증거죠?
55카.
Now I have a 50 MVA transformer. But you see that I have a radiation index very high. So in fact, the normal case is not 5. The normal case, what they use
4.
is 4. So you design
4.
for 4. Doesn't want to change. Okay. So 55 MVA.
좀 TR 있는 건 좀 다시 봐야 되겠네요.
Yeah. So you design it for 65, no, 60. Yeah, for 62 kA. All right. Now you want to have 5. So you will have to increase the transformer tap, yeah, to 500 volts. Of course, you will need 50 MVA plus 5% or 10%. Yeah? You design the current for the normal case, and you increase the number of taps.
Yeah.
Yeah, you increase the voltage in order to get the power you need for 5 degrees per minute. Yeah, but in this case, maybe I have to change the arc efficiency because it's going to be a long arc.
다시 잘 생각해보겠네.
Yeah, I've decreased the arc efficiency, yeah. So it's going to be a 62 MVA transformer.
How about using the 55 car?
And
55.
55 kilowatts. So it's a 60 MVA transformer.
60.
Yeah.
전력이 얼마입니까? 지금 변할게요.
45.
45.
45 광양도 320이에요? 아니 300톤인가?
아니, 있니?
예?
있니?
시간이.
아니 그 광양이 있는
강연
게
280이지.
280이에요? 광양이 한 42MB 쓰고 화학계 분에 이재강 것도 45.
But I consider in this case, yeah. Because this is a huge ladder, yeah. During heating, I consider 1.4 degree per minute heat losses, which is maybe too much, because it's a big ladder. So okay. So it's going to be 55 MVA. But still, you see, the radiation index is very high.
Okay, maybe we will check again, yeah? And we will keep going the procedure.
Yeah, but it's good exercise, yeah,
Yeah.
to show you how it
Well,
works.
I think we would like to know that how to the index, how to change the index, yeah?
How to change the index?
Yeah.
Just you change the current.
The current only. Do you change the several factors in the table?
Huh?
You changed several factors, refractive index and arc current and so on.
You don't change anything, only
Anything?
here you just change the current.
So, and I want to...
Because the driving factor is the heating rate, what you want to achieve. So the heating rate is driving the arc power, what you need. Yeah.
How about 4 minutes? 4 minutes.
What?
4 degrees per minute. Yeah, how much arc we need arc power?
37 megawatt.
In the case we can use 45.
Huh?
45 MB.
Yeah,
우리 지난번에
47.
네?
우리
47.
지난번에 정도 됐던가? LF?
37요?
내가 됐던가? 그래서 1.7 하면 얼마인데? 77, 49.
야.
당신은
크게 나온다.
크게 나와요, 그죠?
47 MVA.
It's a little bigger than our calculation for the electronics. We have the simple calculations program. Is it bigger?
지금 쓰고 있잖아요. 45mm. 330톤. 그 혹시
But don't forget.
300톤으로 지금 간 거 아닌가요?
300톤.
330톤으로 했으니까.
그렇게 생각하지 않았을까?
Okay.
아.
I mean, I'm very flexible. See, 42.
아마 준 거지.
왜 이러면은 좀 곤란하지.
No,
이 차를 60가 썼네, 김과장.
어?
이 차를 60가 썼네.
차를요?
커런트가 42에서 50까지 쓰고 맥스가 60을 썼네.
맥스 60.
The existing plant is the current. Yeah, we used 42 to 50, and max secondary current is 60 car.
60.
The existing plant,
Yeah,
we used 42
yeah.
to 50 car
Kiloampere.
kiloampere current,
Yeah.
and max secondary current is 60
And
60 kiloampere.
what is this? 60?
Max secondary current.
Max.
Maximum?
Yeah,
Maximum.
So it's a.
Heating time is 20 minutes. Heating time is 20 minutes.
4 fois de 8. So you need to reheat by 80 degrees. It's a lot, huh?
No, but the maximum is 20 minutes.
But this is the model, how the way the model is calculating. This is the arc power, what you need to develop by the arc. Yeah. So you take the heating rate plus the temperature losses. Temperature losses is considered as 0.6 for this big ladder. Yeah. 0.6 degree per minute. Time the tons. Time steel capacity, heat capacity. The steel heat capacity
Okay.
is 0.24 kilowatt hours per ton of degree C.
Okay, sorry. How are changing the heating time? It's 10 minutes. 10 minutes. Not 10 minutes.
No, you fix the heating rate, and this is fixing the power you need. So the heating time has nothing to do with the transformer capacity. If you heat during 10 or 1 hour, 10 minutes or 1 hour, it doesn't make any difference.
I misunderstood. 계산한 게 어쨌든 모르겠다. Okay, shall I start again? I will check.
No, but we are discussing about this model and the validity of this model. So I explain you how it does calculate. Again, I start 4 degrees per minute. Then you have the heating rate and the temperature losses. Yeah, the temperature losses are given here. Okay, so you have the degrees per minute and then converted into energy. So the kilowatt hour you need per minute. So then you have the kilowatt hour divided by the arc efficiency. Arc efficiency in this case is 70%, which is optimistic, and then divided by 1200 megawatts. So I have 32 megawatts necessary
32 megawatt.
on the arc power.
Power.
So this is the first thing you have to check with your calculation.
저 잠깐 스크린 봐줘. 잠깐만. 우리가 계산한 거 따를 수 있겠지.
지금 31.7은 심플하게 지금 계산하면 되나?
우리가 실제 분당 전기차를 여기 26메가와트 나오거든. 지금 31.7메가와트 나오는데.
그럼 뭔 차이나?
응?
그건 차이나?
실제 차이는?
그 차이는
이렇게 계산을 해가지고 하는 거지.
용광부 뭐 CP가
잠깐만, 이거
얼마나
틀린 거 보자. 0.6도씨, 0.6도씨. 우리는 뭐 저런 거
그 스틸 카패시티는 얼마 썼습니까?
응?
스틸 카패시티
320톤,
아니
330톤.
그게 아니고 비열 톤당 1도씩 올리는 거
비열?
그냥
비열
0.24.
4점 비열 4.86kg
아크 이피션시 고려했습니까? 아크 이피션시
그걸 다 들어갔지.
다 들어갔다고. 옛날 우리 내들 그 봤을 때 아크 이피션시 이런 거 고려 안 한다.
해가 들어가지. 노용 배낭 손실, 뭐 전력결정 효율 뭐 이래가지고.
아크가 발생한
그러니까 그렇게 쓰면 연도들은 들어간 거지.
그래요.
그렇지. 한번 보자.
So you get the same value?
I have to check it.
차량 계산한 걸 보여주시죠.
그렇게 보여주려고 뽑아달래 나보다 안 보여주잖아.
이걸 받아달라고요?
I would like to know this is I would like to know it is right or not. But we used this calculation for this is simple, very simple. Korean.
Yes.
You can see, yeah?
This
This
one.
is 30 ton.
You are calculating in kilocalorie per ton and degree C. My God.
You can see, know the
스페시픽.
So made it in kilowatt hours per ton. Made it in kilowatt hour per ton and degree C. The CP.
CP 값부터 좀 봐야 될 것 같은데
위.
0.87
예.
저거 킬로칼로리를 킬로와트 아워로 바꾸면 0.87 킬로와트 아워.
This is arrival. This is the final 10 minutes. And this is
Calculated, yeah.
calculated 4 degrees per minute. We need it.
Mhm.
And this is only second.
Yeah,
Yeah.
if you want, yeah.
This is a drop. We the compensated drop.
The temperature drop, yeah.
Yeah, temperature drop.
1.5, it's a lot. Yeah.
And this is the kilowatt hour.
Yeah.
And this is for kilowatt per minute.
Yeah, come back to the kilowatt hour.
Yeah.
Click on top in the formula bar, yeah.
Hmm?
There?
Yeah.
No, in the 319.
This.
Yeah, but you take the kilocalorie per ton and you can. No, this is not good, my friend. This is not in kilowatt hour. This is in kilocalorie or whatever.
No,
This is not kilowatt.
can I check it? I don't know. I started a long time ago. I didn't remember.
Okay, you see, yeah? You take the kilocalorie per ton and degree C.
Yeah. But it's inside of the transformation
Where?
application. I don't know. It's a simple calculation. I have it. So and this is kilowatt per minute.
No.
And
No, cannot be, wait. You take the 319,
this is only 60 seconds.
B12, yeah.
Minute.
But what are you doing? You take the required energy.
3,600.
3,600이에요.
곱하기 3,600.
6시간이 분이잖아.
아니요, 킬로와트라는 게 세컨드.
곱하기 3,600.
세컨드라는 거예요.
이게
36,
36배예요?
예. 3600.
이란 말이 안 된다. 아니야, 이러면 50%지.
뭐 잘못됐죠.
뭐 절대.
45.
그대로?
맞죠. 저 위에 건 틀린 거 아니에요. 맞아요.
킬로와트 아워에 킬로와트는
3,600
초에 초. 분이 아니고.
이제 내가 지금 이제 연결되고 40분 나오는 거 아니에요?
45 나온다.
And this is transformer efficiency and temperature, heating efficiency, and here the heating ratio. And this is consuming.
Yeah, I cannot check anything. You are going too fast. Yeah.
지금 냉각이 많아 안 보이더라고.
뭐 이래 구하면 오래전에 스킵 잘하면 하면은 이렇게 나온다.
45.
아니 아까 3,600 안 곱하고 60 곱해도 40원 나왔었나요?
아까 이거 등식으로 이게 연결 안 됐나요?
여기 연결 안 되고 다른 키로줄 이게 연결돼 있고 이게 연결돼 있고 하도 오래전에
그거 보면 되겠네.
이렇게 돼 있네 이렇게.
거기에 뭐 연결돼?
And this is only the showing you. only and here this is this and
MC T 됐고요. 그게 저 연량이라 성원시 필요한 연량. 네, 그거 치고 그러면 쳐서 보면 되지.
그것도 안 뚫리지 봐도 엑셀 있는지 아까 시간 줬어.
저 회사는 냉각수 손실 연량 저런 거 볼 필요가 없는데 지금 상황에서는.
응?
19155가 성원에 필요한 에너지, 전기 에너지로 들어가야 되는 건데 저게 킬로와트거든요. 19155가. 그러면 나누기 1000 나누면은 20메가와트네. 20메가와트.
그래 그거 있는데 리얼스 또 이거 곱해지겠지. 이게 29. 여기 오자는 게 여기 올 때 열손실량 큐 있잖아요. 열손실량을
네.
해가지고
네.
냉각수에서 얼마나 손실량이 생긴다 더 해가지고
예.
그 소실 여기서 이제 올라가는
22메가와트.
그래 이 20이 나왔잖아 여기 22에서 또 손실 보상 계속 여기서 또 들어가는 거야.
28,
80에서 28 전력계도 왜 이래 되는
44.
This is heating 열량은 뭐라 그래요?
히트.
어?
히트.
열량 히트는 we need this heat quantity
발륨이지.
heat volume.
I need 31.7 megawatt in arc power. What is your arc power?
Yeah, in here is no, it's only the we calculate transformer capacity.
Here 28 megawatt. 28 megawatt.
This is megawatt.
네. In terms of mechanical.
This is the
Aspects.
coefficient to compensate.
I don't
the
care
losses.
about coefficient. Just ask you the
20
arc power you need.
megawatt.
20.
What is the arc power you need?
22.
22.
세상 28인데
Yeah, you are very optimistic. Yeah.
Yeah, and
Although I have 0.6 degree
Yeah.
per minute temperature drop and you have 1.4. So that you have 1.4 temperature drop, I have 0.6. Yeah? 1.5 even. And I can find only 31.7 and you have 22. How can that be? I mean, I'm sure that your still heat capacity is very low. What is the arc efficiency?
efficiency를 뭐로 봐야 돼요?
이걸로 봐야 되나? 지금 뭉뚱이가 나서 뭐라고 말하기 어렵네.
이거 하고 저거 하면 피부가 하기가 그렇네.
이게 이제 그게 이제 멤브레인 넣고 하기 위한 크게라는 얘기는 이게 이제 SMS도 이렇게 계산을 해요. 간단하게 계산할 때. 오케이. 오케이, forget.
Never mind.
시간이 결혼해야 되니까.
No, but you have proposed already this transformer. Eh? You have proposed already this transformer.
뭐야?
이거는 제안합니다.
This is the existing data. We already do the 1, 2, 3 level points. We already used it.
Uh-huh.
From 22 MBA 1, it's 100 ton. 1 to 20.
And
18 MBA, 18 MBA, 20 MBA. I remember.
You have cross-checked your calculation with the result what they have?
Yeah, but at that time I'm not in charge of the leather furnace, but
To calibrate your model.
and we checked it with the furnace supplier, and then we used this simple calculation for only the calculate the transformer capacity for our purchase.
Now, because I mean, I'm using this model since about 15 years.
Yeah, I think so.
So
15 years ago.
yeah.
그래서
아니 그런 게 아니에요. 그런 개념을 얘기하면 안 되고 그냥 간략하게 이것저것 지금 다 모르니까 비율로 0.8, 0.7 이래가지고 곱해가 쓰는 거지 경험치로.
I'm surprised about your figures that you need only 22 megawatts. 22 megawatts measured on the secondary side when I need 31 or 32 megawatts, 10 megawatts more. This is a big difference.
So the one more coefficient is I can translate English, but the compensation coefficient for loss 0.81. Yeah, and then finally we consider all the chemical losses. Yeah, and then we finally 28.2 megawatt, and then we consider the electric lines efficiency and transformer losses, and then
Now I'm talking about a very simple thing, Mr. John. To increase 4 degrees per minute, at the arc you need to supply 31.7 megawatt without any losses considered later. And this is just this 31.7 is coming for little parameters, very little parameters. This is just the heating rate, the temperature losses, which is 0.6, yeah, the steel CP, and the arc efficiency. Steel CP is here, kilowatt hour per ton and per degree C.
그러니까 최소 저거 이상은 나와야 되는데 저거보다 작게 나오면 그 말이 안 된다.
지금 자기 생각이고.
And I guess
이게 데이터가 맞는가 보려고.
And I guess the mistake is coming from this parameter.
I have to check it.
So,
I have to check it.
저기에서 우리가 말할 수 있는 0.24가 스틸에 대한 고정값이거든요. 엔탈피.
그런 얘기가 다른 거 아니야. 이게 맞고 틀린 얘기가 아니야. 사이즈 용량을 보는 거야. 오케이.
계산 사상이 완전 튼 거예요. 그렇게.
그렇지. 이건 이제 구매용으로 그냥 간략하게 계산하는 거 만드는 거지. Okay, I need a time break 5 minutes.
Okay.
So because of someone's come.
Okay, no problem. You need a time break.
자, 그대로.
예.
다시 10분 주자. I found it, the history CFG file in your C directory. C directory.
Yes.
History file. It is needed.
무너진다.
The C programmer, yeah, okay. And then intern. Here, this is it.
This you need. Okay. Give me that.
It's a copy again. The history, the folder has the same address is needed.
So I send everything.
Okay, thank you very much.
정말 어떤